Alright, so now it's time to finally dive into microbiology. The only other microbiology videos I have on the channel are pretty much from last year's book. They're from First Aid 2018, and I don't have the sketchy micro stuff or the actual book in front of the screen, right? So now what's going to be different this time around is that I will have my own personal annotated PDF on the screen. If you're looking to buy my PDF, obviously anytime, feel free to email me. My email is on the information below, usmle.live2018@gmail.com. So yeah, I'm going to be doing this entire stream with the book on the screen, going through bacteriology right now. First things first. And as I go through bacteriology, for each bacteria that we visit, I'm going to have the sketchy micro image there so you can see the final sketchy micro image and what you're supposed to recall from it. Now, I still highly urge, obviously, that you go ahead and do sketchy micro, purchase it, because it's a whole different experience when you actually get to see them drawing it while they talk about what each drawing or each part of a drawing actually represents. So that's different from what I'll be doing right now, where I'll show you the final aspect of the whole image and just the final product, and give you the story of what each aspect of the picture actually gives you. Okay, so we can get started now. First things first, basic bacteriology. Now, you do get questions on these things, right? Oftentimes you get questions that are either going to be direct on the bacterial structures, especially on the envelope and the difference between gram-positive and gram-negative, or you'll get information, where they'll tell you stuff about a bacteria, and then based off of that information, you should be able to infer other data from it. So first thing they talk about are the appendages bacteria can have. There's either going to be flagella or pilus or fimbria. And these things are pretty much giveaways. Like if you see flagella, they're motile, right? And pilus and fimbria, these are glycoproteins, and these are literally used mostly for just adherence, right? Mediate adherence of bacteria to the cell surface. The sex pilus forms during conjugation, and we're going to see that when we get there. A spore is only found in the gram-positive bacteria. So if you ever see a bacteria that has spore to it, you know that it's gram-positive, right? So that's what I mean by taking information and being able to infer other information from it. And a spore is always keratin-like, right? It's going to have this dipicolinic acid in it. And of course, this is another thing that if it's given in a question, you can infer that's about spores. Spores allow survival. They're there for resisting dehydration, extreme heat, and even chemicals. They can actually get through your digestive tract and actually come out just fine. The last thing are your cell envelopes, right? So this is what they show you at the bottom over here. There's only two different real divisions between the two. You're either going to be gram-positive, where you're going to have the lipoteichoic acid as well, or you're going to be gram-negative, and you have something called an outer membrane, right? Two membranes, an inner membrane and an outer membrane with the periplasmic space. So let's take a look. Capsule, first things first, right? Organized, discrete polysaccharide layer, except the poly-D-glutamate that you see in Bacillus anthracis. And when we get to Bacillus anthracis, you'll see in the sketchy micro image, there's a very nice button system. One of the guys is wearing a bunch of buttons that are poly-Ds. The buttons all spell out letter Ds. And capsules just protect against phagocytosis. That's so a lot of things, when they lose their capsule, now they can be phagocytosed and gotten rid of. There's something called a slime or S layer, right? The S layer is a loose network of polysaccharides, and it mediates adherence to surfaces, especially foreign surfaces like indwelling catheters. Right? So a lot of bacteria, especially, well, all of these guys, bacteria, parasites, viruses. For now, we're talking about bacteria. So a lot of bacteria are, you have to associate specific scenarios to certain bacteria, especially when it comes to pneumonia, right? There's so many different bacteria that can cause pneumonia. You really need to identify what is the most likely causative agent in specific different populations, right? Whether it be a mother, a kid in college, or it be someone in the army, or someone who's just always drinking and they're an alcoholic, right? Different scenarios present with different, most likely causes of pneumonia. The next thing you see here is an outer membrane, which we just talked about, right? It's gram-negative only. They're the only ones that have an outer membrane, right? That's kind of what defines these two guys to be different from each other. So the gram-negative guy with his outer membrane looks like this, but the other one, gram-positives, they have a really thick cell wall, right? So you can see both of them have a cell wall. Don't make that mistake to say that a gram-negative bacteria does not have a cell wall. They do, it's just really thin, right? Whereas here you can see it's triple the size according to this image. So that's one thing you want to definitely understand. And they go on to tell you that the outer leaflet contains endotoxin, which can be lipopolysaccharide or lipooligosaccharides, embedded proteins like porins and other outer membrane proteins, and an inner leaflet that has phospholipids, right? And you can see all of that here. So you can see this this porin protein right here. There's endotoxin, which can be lipopolysaccharides, right? And then in between the outer and inner membrane, more specifically in between the cell wall, the peptidoglycan cell wall, and your inner membrane, you have your periplasmic space, which is exactly where beta-lactamase is found. So beta-lactamase inhibitors work at that site. And I have seen questions where you get a diagram giving you the gram-negative cell membrane layout, and they're pointing at different points of this image, just like you see these lines are pointing at, and they'll ask you, where do beta-lactamase inhibitors function, or where do they carry out their abilities? And it's going to be right here, between the cell wall and the inner cell membrane. They then go to tell you endotoxin, like lipid A, induces TNF and interleukin-1 activity, right? So that's going to be fever and stuff. Antigenic O-polysaccharide component. Most OMPs are antigenic. And then the porin is the thing that's allowing you to have transport across the outer membrane. That's your little porin right here. So there's no porin in a gram-positive guy. So things just come out of that one membrane and can exit, right? But you have a big cell wall, all right? Periplasm is the space between the cytoplasmic membrane and the outer membrane in gram-negative bacteria. Peptidoglycan is in the middle, which is your single cell wall right there. Accumulates components exiting gram-negative cells, including hydrolytic enzymes like beta-lactamases. Right? So medications targeting beta-lactamases work in the periplasm of gram-negative bacteria. The cell wall itself, peptidoglycan is a sugar backbone with peptide side chains cross-linked by transpeptidases. It's a net-like structure that gives rigid support, protects against osmotic pressure damage, and that's what you're seeing over here. Right? It's much bigger, much more active in the gram-positive bacteria compared to a gram-negative. Last thing is your cytoplasmic membrane, which you have your phospholipid bilayer sac with embedded proteins like penicillin-binding proteins and other enzymes. Lipoteichoic acid, which is let me see right here. See, is only found in gram-positive. Lipoteichoic acid only extend from membrane to the exterior, right? So you can see it's on the outer part of the membrane, and then they come all the way outside. They don't extend inside though, and that's literally just about the lipoteichoic acid. This one right here, the orange one. What they both share though, these other squiggly lines, what they both share are the pilus or the pilus and the flagellum. Those things are shared by both guys there, all right? So cytooxidative and transport enzymes, penicillin-binding proteins, lipoteichoic acid specifically induces TNF-alpha and interleukin-1 activity as well, just like lipid A did that in gram-negatives. Right? So gram-negatives had endotoxin, right? Lipid A induces TNF and interleukin-1 activity. Gram-positive guys have lipoteichoic acid, which also induces TNF-alpha and interleukin-1 activity. Right? Bacteria do not have mitochondria. Their electron transfer chain happens in the cytoplasmic membrane, which is the reason why we think that mitochondria are actually two bacteria living together. Like some bacteria ingested another bacteria, and that second bacteria that was ingested was the mitochondria. And they started living together and worked out. Pleomorphic bacteria are a third different type. These guys don't have rigid cell walls, so examples include anaplasma,